In the cathedral quiet of dawn, the sun's first slanting rays gild the top spires of a great city. A new day is silently sweeping westward. In the canyon streets, dark still lingers. Most of the city is asleep. The new day moves slowly westward. Gradually, the city comes to life. Thunderous, dynamic is the city, awake and alive. Yet at the heart of the pulsing metropolis, there is calm, massive shapes in polished cases. A man in a bank of shining gauges in a monotonous hum. Yet here is created the force that energizes the city, the electric power that gives it life. This is the heart of the city. In the control room, that never-ending undertone is translated into the demands of the city in action. 10,000 or 100,000 housewives go into action with vacuum cleaner and washing machine. And on the river, an outbound ship bellows for right-of-way. In the bridge tower, a man moves a lever, and the giant span rises easily and surely. There's no thought of failure. Of course there'll be power to lift those thousands of tons skyward. So the big ship approaches and passes without slacking speed. Power, abundant power, instantly available, whatever the circumstances. A summer storm rolls over the city. Almost without warning, the city is shrouded in gloom. There's an urgent demand for more and more electric current. A critical challenge that must be met, and is, through the flexibility of modern power production. Thus, the ebb and flow of the great city, working and living, are reduced to the simple terms of load on the line. Drama written on the faces of meters and gauges, set to the unending music of the turbine generator. As we magnificent Americans go bustling about our day, do we ever pause to consider this miracle of electric power by which we live? Are we impressed? A little humbled? Of course not. We take it for granted, confident that it will always be untapped when needed. To what extent this vital, abundant power has advanced our civilization, no one can say. What would happen if suddenly it were to fail? No one even dares to think. But what manner of magic lies inside that polished case? What sort of marvel is this? Well, paradoxically, it's one of the simplest principles of converting fuel into useful power. Coal, oil, or gas is burned to transform water to steam. Steam, under pressure, is directed against a sort of windmill, thus transforming heat energy into mechanical energy, which in turn is converted by the generator into electricity, completing the transition from fuel to usable power. And because of its smooth rotary motion, apparently reliable and long-lived. Through the years of advancement in design and manufacturing efficiency, that simple principle has been developed into intricate and complex operational form and into many challenging problems. The elementary windmill has evolved into a series of wheels fitted with thousands of buckets, precisely shaped to extract maximum energy from the steam. And the result? Today, a handful of fuel does more work than a strong man can do in 3 days. All you hear is a gentle hum. But inside the turbine is raging a superheated tornado, whirling the massive rotor 60 turns a second. Steam at bullet speed, stripped of its heat and energy, red hot to room temperature in a split second. Such performance might seem a miracle to everyone but the men who created it. It's a big brute, sure. Yet in spite of its size, it is built to standards more exacting than those of the finest watch. A precision of heroic proportions. No other mechanism operates so continuously, so reliably, under such heavy loads, and with so little care. We regard our automobiles as highly reliable, and they are. But imagine driving your own car 500,000 miles a year, full throttle, wide open, day in, day out, year after year, for say 30 years, with maintenance expense totaling, a dime for every 10,000 miles. Fantastic? Of course, for even the finest car. Yet just ordinary for a turbine generator. Thus, the simple power conversion principles becomes the mainspring of the modern age. All progress begins with ideas, and every new idea, every bold new line of thinking poses problems, questions that must be answered. How do we know what happens inside a turbine? How does steam behave in the labyrinth of passages at 1,000, 1,500 miles per hour? The answers are found through exploration in the air test laboratory, which is to turbine design what the wind tunnel is to aircraft design. No guesses, only positive answers count. So, working with experimental sections under controlled conditions, high-speed air pre-proves what high-speed steam will do in the turbines of tomorrow. Beyond the soundproof walls, where the hurricane scream is hushed to a whisper, vital performance data are recorded and analyzed. To the uninitiated, this machine suggests something straight from Mars. But to the engineer, it's simply one of the instruments of research, a tool for getting answers. Nearby, other technicians are probing into the future, perhaps many years ahead, experimenting with gases at velocities far beyond the speed of sound. Velocity so high that such phenomena as shock wave are visible. And how do we know which metals will stand up best under blazing turbine temperatures? Well, here in precision furnaces, various metal alloys are being tested under high temperatures and heavy loads, and their stretch measured in terms of atoms per inch per hour. No quick conclusions. Some of these studies have been in progress for months, some for more than 20 years. And out of this patient research are coming new materials, opening new frontiers in turbine efficiency and reliability. And here is another ingenious tool for the study and design of tomorrow's turbines. Technically, it's known as the differential analyzer. Unofficially, it might be called the brass brain. By any name, it's a machine capable of solving mathematical problems beyond the range of human computation. Intricate equations in differential calculus that would keep mathematicians and a corps of calculators busy for more than a lifetime are worked out by this robot in a matter of hours. Thus, mathematical explorations check advanced ideas of design without the waste of trial and error methods, opening avenues to progress which otherwise would remain obscured. Such is the price of progress, exploiting the best of the past, exploring further and further into the future. New advancements, new standards of performance developed and proved in the cold calm of creative engineering, then brought to life in flame and thunder Throughout the manufacturing cycle, there is continuous evidence of critical quality control. A test sample from each forging must pass laboratory analysis before machining begins. Large rotor forgings are center bored through their entire length, and the bore minutely inspected before soundness can be certified. Steel for turbine wheels is cold sawed from billets, then ground, polished, and etched to make sure the material is of prime structure. Even heat is used as a testing agent. Every turbine rotor is heat stabilized and checked to ensure that it will run true under all operating conditions. Various parts so small as to defy ordinary scrutiny are subjected to shadowgraph enlargement and the size and fit tested to master standards. Familiar symbol of critical craftsmanship is the check gauge, varying in form and type to fit every character of operation. But with such a high premium on precision, even the gauges themselves must be frequently challenged and checked. So, in an air-conditioned room of unvarying temperature, are maintained the master gauges, checked periodically with the National Bureau of Standards. To most of us, a hair's breadth represents precision. But here it is commonplace to prepare working gauges accurate to a hair split 100 times. For while the facilities are giant size, and although pieces in work are often ponderous, this background of microscopic accuracy is evident throughout manufacture. The building of a turbine is essentially the making of a fine instrument. Gleaming with the beauty of polished silver the buckets would appear right at home in company with sterling service. However, their polish is not for appearance, but for performance. For steam turbine efficiency has reached such a high level that even a gain of a fraction of 1% will be reflected in fuel savings reckoned in carloads of coal. As manufacture advances, inspection becomes more complex. And again, science contributes strange instruments of detection. The magnetic test unerringly puts the finger on any surface imperfections. Parts under inspection are magnetized and bathed in a solution of magnetic particles. And how does this reveal flaws? Well, that bar actually has a flaw, but so minute you can't see it. Yet even cracks that are invisible through a powerful magnifying glass are completely revealed to the eye of the inspector by this bat. So a constant parade of parts, from the smallest buckets to the biggest shafts, goes through this surface flaw detection procedure. Even cavities concealed under the surface cannot escape. For the searching eye of this million-volt X-ray can see through several inches of steel. Thus, manufacturer progresses constantly within the precise limitations of control standards. As the weeks and months of building, testing, and proving approach their climax, the generator, power partner of the turbine, also grows to completion. Finally, the drama of creation nears its end. Tested and pre-proved, piece by piece, unit by unit, the principles assemble, and the stage is set for the finale. At last, without fanfare or applause, it happens. Live steam is admitted. The turbine becomes alive and begins its test run. Yet, even as this is the conclusion of one story, it is but the beginning of another, the more dramatic, more important story of unfailing service in the production of electric power. History will long remember the arsenal of democracy, but few will give thought to the turbines that provided the power to produce the ships and planes, the tanks and guns. 6 times the power of World War I. Power requiring fuel far beyond the nation's capacity to produce or to transport, had not power plant efficiency doubled and tripled. Afloat, the turbine has been a weapon no less potent than big guns. Here, brute power is paramount. Power with economy, higher efficiency. to enable the fleet to range over greater distances, carry more armament, more fighting power. Throughout this mightiest navy of all time, 65 of every 100 fighting ships were driven by turbines bearing a familiar insignia, outstanding evidence of the Navy's faith in the dependability of these turbines, of confidence in the people who built them, people who have as their tools the knowledge, the resources, and the skills of half a century of turbine leadership. That knowledge and those skills are more valuable than ever today as mankind faces its greatest challenge. The development of atomic energy, not as a destructive force, but as a great factor in building peace and prosperity. Not as a bomb, but as a source of electric power. How? Most probably by using the energy of the atom as heat, and the heat in turn to make steam for driving turbine generators. Thus, someday, when scientists have solved the problems, atomic energy will serve the same purpose as coal or oil or gas in our generating stations. But the turbine will be more important than ever. So as you and I go about our daily work and play, with now and then a questioning thought about the future, let us remember that behind the countless motors and electric processes of industry, behind the rolling wheels of mass transportation, behind the marvels of modern communication, behind the gleaming windows and business machines in our citadels of commerce, behind the sophisticated sparkle of famous streets, yes, behind the pleasures and routine tasks in our homes, behind all these is the turbine, will be the turbine, humming its quiet song of service. A thing of wonder today, even more amazing tomorrow. Master creator, that power by which we live.